Otherwise, I'm audible. Hello, hello, I'm audible. So after a huge disturbance, we have finally available to continue. So all of you can see my slides. So we have started our discussion on laminar flow, and we have seen the difference between the laminar flow as well as turbulent flow. Here we would like to take a few more things in the laminar flow. Yes. Note down Reynolds number. So many of you are aware of this particular number, right? A very important number. It is the ratio of the inertial force to the viscous force, right? In the fluid is called Reynolds number, and it is expressed for the internal flow in a circular pipe as something like this. Now, what is the inertia force? Inertia force, we know that mass into acceleration. So, can we write mass into acceleration in something v by t in a particular velocity and time format? Acceleration can be written as dv by dt, but I'm writing in absolute sense v by t. And we know that mass is what? Volume into density. This is velocity by time. So once again, what we can write volume as area into length scale, velocity by time. This is not volume. This is velocity by time. This is velocity, velocity. So here what we have area. Now area. See, I'm representing everything in terms of some length scale. So area can be represented like L square, L square, L by T. This L by T will become velocity. So that will become velocity square, because this velocity will become velocity square into rho. So finally I can write rho LC square V square. This is my inertia force. That is a resultant of all the forces. All the forces in the sense we have many forces, right? Inertia force is nothing but summation of all the forces. All the forces means viscous force. Tell me guys, what are the other forces you encountered? Pressure force, then we have gravity force. Yes or no guys? Understanding my point? So in all together we can write summation of all the forces, that is nothing but the inertia force. And I have, see, I know that area can be anything, but in a very general sense I'm writing area. Area means what? Meter square, right? Meter square means what? I can write this L into L like that. So don't think that this is a some square cross section I'm talking about, or some other cross section. No, in a very broader sense I'm just writing area as L square or LC square. And what about the viscous force? Viscous force, we know that mu into V by H into area. Again, viscosity can be written as mu, and area once again can be written as V by H. Let me write this to be okay H, and this is to be L square. So what you will be getting here, H, instead of writing H we can write LC once again, because in terms of meter it will be same. This will also be L, so this will cancel out. So mu into V into LC. Instead of writing L, let it be denoted by LC. Now when you take the ratio, what you will get? Inertia force to the viscous force. So rho LC square VC square divided by mu V LC. Sorry, this is not VC, rather say this is V. So what we can write, Reynolds number, rho LC V by mu. And what is the LC formula? We have seen in our last class, means in the first class, that 4 into cross-sectional area by perimeter, wetted perimeter. Obviously, for a circular cross-section, the LC will be diameter, and when you substitute there, you will be getting this formula. Remember, V is nothing but not the maximum velocity. V is nothing but average velocity. Here, V is what? Average velocity. Remember that. We are not talking about individual fluid layer velocity. We are talking about average velocity of a control volume through which many fluid particles may have been passed through that particular control volume. Now, so from where to here, how we are going? We can also write this mu by rho. You know, V average into D mu by rho. This is what we know kinematic viscosity, and that is what they have represented. For a circular flow, note down, when the Reynolds number is less than 2300, we say it's a laminar flow. When it is in between 2300 and 4000, we say transitional flow, that is of no use for us. And when the Reynolds number is more than 4000, we say it's a turbulent flow. Once it is done, let me know. I'm just telling you the formula for any particular condition in terms of LC, characteristic length, and what is the meaning and significance. All those things we have already discussed, right, regarding the characteristic length. Getting my point, all of you? Yes or no, guys? Can I move to the next one? Done. Can I move to the next segment? No. So regarding this hydrodynamically fully developed region, we have already discussed that we know that velocity will vary in both the directions, in the radial direction as well as in the axial directions, x and r, right? X in this direction and r in this direction. It will vary in both the directions. But what we say, when the flow is fully developed, then velocity will no longer will be the function of x, it will be only the function of r. And this we will prove that for a fully developed flow. For a fully developed flow. All of your understanding. See, the region beyond the entrance region in which the velocity profile is fully developed and remains unchanged is called hydrodynamically fully developed region. That is a very, very important. See, the velocity boundary layer is start developing from here. and it is keep coming towards the center like this. So what you are observing, center velocities keep on increasing. Yes or no, guys? Till the flow is become fully developed, the center velocity is what? U center. Let me call this to be U center. U center. That is the center line velocity. Center line fluid velocity is keep on increasing till the point the flow is become what? Fully developed. Yes or no, guys? Understanding what I'm saying? Now, once it is done, let me know. Done? Can I move to the next one? Is it done? No down. This one. For hydrodynamically fully developed, dou u by dou r, dou u by dou x will be zero because when u is not the function of x, and when u is not the function of x, so obviously dou u by dou x will be zero. For example, u is nothing but u maximum 1 minus r whole square. When you do the differentiation dou u by dou x, it is zero. So note down one important point. All of you have done with this, right? So what you have observed, you have observed that whenever the fluid is flowing in a pipe, then there is some boundary layer formation will happen like this. Velocity profile will not change. Each and every fluid layer will have the same velocity. But what is happening in the developing region? What is happening actually in the developing region? If I ask you the graph, let's say x is moving like this and u center. What will happen with the u center velocity? Till the flow is become fully developed. This is my developing region. Now, whether u center line velocity will increase or decrease? U center line velocity will start increasing and it will increase till it will become fully developed, and after that it will remain constant. It will remain constant, right? The means all I can say, not exactly like this, because you have to show some uh, increment value in that till it is becoming developing like this. Central and velocity will keep on increase. What about this wall shear stress with respect to x in both developing and fully developed region? So what is going to be happening? I'm talking about developing region first. It will decrease. It will decrease, and then it will become constant. Here also it will become constant. Why? What is the wall shear stress formula? The wall shear stress formula, everyone know that mu into du by dy, right? For example, if I talk about the boundary layer thickness, let's say this is the boundary layer thickness delta, right? So what we can write? Mu velocity I can write as u center line velocity divided by delta. Delta is a boundary layer thickness. Boundary layer thickness. And what you are observing from this point, from here, that wall shear stress. The wall shear stress we can write mu into du by dy. That is mu into uc. That is the center line velocity. The center line velocity divided by delta. But generally, why the wall shear stress is start decreasing? Because center line velocity is increasing, but delta is also increasing. See that delta 1, delta 2. But as compared to u center, delta is increasing at a rapid rate as compared to u center line. So overall, it will make the wall shear stress to decrease. As we march along the x directions, it will decrease. Right? So make a note of it. These two graphs are very, very important. Even you can plot it for complete this. They can ask in gate exam what is happening in the developing regions. For a fully developed region, everyone know that, right? But what is happening over here, that is the main thing. Because for a fully developed region, wall shear stress can be written as mu into uc divided by delta, for example. Then this is constant, this is also constant. See that delta will remain constant. Delta will remain constant. uc will remain constant. Nothing will change. So that's why it is a constant. What about dou p by dou x? In a fully developed region, what about dou p by dou x? That is slope of p versus x. If I can plot from here to here, like P versus X, pressure versus X curve, then what will be there? It will be like this. This is a straight line. There is some other variations. Some other variations. That means what I want to say, dou P by dou X, dou P by dou X will become constant in fully developed region, and it will continuously changing its slope in the developing regions. Why it will be constant? Why dou P by dou X is constant? Because u center line velocity is not changing. U center line velocity is not changing in the developed region, but in the developing region u center line velocity is keep on changing. So the dou P by dou X will also be start changing accordingly. And because of that only, this why there is a center line velocity is increasing, because of dou P by dou X only, because of dou P by dou X variations, right? So no. Why it can be zero? How it can be zero? How dou P by dou X can be zero? There has to be some pressure difference, right? When you put the pressure gauge in the developing region, always it will show the reading more than the developed region. Always pressure will be continuously decreasing because of decrement in the dou P by dou X, right? Because of decrement in the dou P by dou X, monoatomically or some other variation than straight line, what is happening? U center line is keep on increasing. See that? Once that driving force, that is dou P by dou X, will become just constant for every instant, the u center line velocity will not be changing. But before that, dou P by dou X is keep on decreasing. But after that, it will be remain what? Constant. The slope of this one, what will happen with the slope of P versus X? Dou P by dou X will remain constant is for a straight line. Right. This graph maybe you can ignore, uh, that they may not ask, but this two graphs is very important. Till now they have not touched this particular part, but they can ask at any point of time. For flow to happen, some driving force would be there, right? And what is the driving force for the u central line velocity? Dou P by dou X is keep on decreasing at a very like a rapid rate, but further it is not decreasing, it is constant. Gap is there, means a difference is there. Dou P by dou X difference is there, but that difference is constant for every instant as we march along the x directions. That's why central line velocity is not fluctuating; it will remain constant like this. Now, once it is done, let me know. Done. Dou P by dou X, if you are saying zero, then what is the meaning of that? Pressure is remain constant. Is it possible? Let's say we have the constant diameter pipe where velocity cannot change. Constant diameter pipe means what will happen? At this section, at this section, velocity will remain same, average velocity, kinetic energy will remain same. According to Bernoulli principle, how the flow will happen? When total energy, see, when total energy at any segment is more than total energy for a section like this. Suppose, for example, here to here we have some variations in a particular energies, then only the flow will happen. Yes or no? Or maybe you can think of total energy remain constant according to Bernoulli principle. If there is a no head loss due to friction, there is a no loss, nothing is there. What is happening? How the flow is happening? What do you think that? As the diameter is not changing, so velocity will remain same, for example. Then how the flow is happening? Total energy is what? P by rho g plus v square by 2g plus z is equal to constant. Z, there is a no variation of height. The pipe is not like this. Pipe is horizontal. Z is not there. Gone. V is not there. Then who is contributing to that? How the flow is happening? What do you think? Pressure energy only. Because of the pressure difference only the flow is happening. If you think that dou p by dou x will become zero, then pressure will be constant. Then how the flow will happen? Getting my point, all of you? Now, note down the laminar flow. That is the first case we are discussing. A very first case, that is a laminar flow in a pipes. Note on the small figure which are shown in the figure. Yes. And that too you know that total energy cannot remain constant in a flow in a pipe, right? Whenever the flow is happening from one segment to two segment, for example, everyone know that in whole universe we have the viscosity for every fluid which is being attached to the water, for air, anything. Definitely there is a head loss due to friction, and that is what we will come to know today. Definitely there is a head loss due to friction. Nobody can deny from the fact. When there is a head loss due to friction, you know that whenever you are giving some energy, 10 suppose watt, definitely we will not be able to achieve here fully 10 watt. 5 watt will be lost, right? Some head loss due to friction. That much of extra energy I need to supply from the pump. That much of extra energy I need to supply from the pump. So definitely total energy, this 10 watt is total energy. That is pressure energy, kinetic energy plus potential energy, always higher than any other segment when you march along the x direction in a flow through a pipe. So definitely you know that when the total energy here is more than total energy at 2, because head loss due to friction will be encountered in that, then how can you say that when velocity energy is not contributing, when potential energy is not contributing, then how can you say total energy will remain more than at one section as compared to the second section? Definitely pressure energy, right? Pressure energy at point number 1 is more than pressure energy at point number 2. That's why you have dou p by dou x exist. But in a developing region it will keep on fluctuating. Maybe I don't know the variations, right? That will keep on fluctuating, but in a fully developed region that will remain constant. Getting my point? That will remain constant. It doesn't mean that there's no pressure difference. There is a pressure difference. If you're saying dou p by dou x is equal to 0, then only you can say pressure will remain constant. If pressure will remain constant, now tell me 2 to 3 again there is a head loss, then how total energy at 2 will be more than total energy at 3, because kinetic energy gone, potential energy gone, which is contributing towards total energy now, potential energy, this pressure energy. Then definitely pressure energy has to be more at point number 2 as compared to point number 3. Getting my point, all of you? And that's a very ideal situation when we have the pressure energy also constant. That means there is a no head loss due to friction. There is a no power gone. Whatever the power you're supplying, exactly you are able to flow like anything. Like, means you can imagine some fluid which is flowing in a nanotube pipe, carbon pipe, where you have a fully smooth surface finish, right? In fact, there also it is not possible to achieve that condition in reality, but still I'm saying to imagine where the total energy remains constant at all the points in a fully developed, remember, in a fully developed. Now, so what is happening when the laminar flow is happening in a pipe? Then what we can have here, we can write for a small fluid segment. For a small fluid segment, everyone know that whenever the fluid is flowing in a pipe, then what will happen? there will be some forces which is being encountered by the wall onto the fluid in these directions. In a circumferential directions, it will apply the forces because fluid is offering some resistance in this direction. So what will happen? The wall will offer some kind of resistance to this particular fluid element. And how the variation will be? The variation will be tau into 2 pi r into dx. I am assuming that element is what? Dx, and the radial distance from a center line will be taken as r, right? So for this particular element, my different, what are all the pressure variations? Here we are applying pressure into what? What is my area? P into pi r square. And what is my area here? What is my pressure variation? P plus dou p by dou x into dx into pi r square. Capital R is a radius of pipe. Small r is nothing but the radius of elemental area which I have considered. This elemental area. This particular elemental area of dr thickness. Now you can balance net force, that is equal to mass into acceleration. And net force, you know that pressure force plus viscous force in the direction of motion. What is my direction of motion? Like this. That is equal to mass into acceleration. Acceleration in which direction? X direction. What is my acceleration formula? You know that. Everyone know that. This is the formula we have. And I'm discussing for study flow. So this will be gone. And we are developing for we are developing this concept for fully developed region. So dou u by dou x will be 0. So the total term will be gone. The total term will be gone. And the pressure force and the viscous force we have to balance. Pressure force, this is acting in this direction, in the direction of motion, positive, minus p plus dou p by dou x into dx into pi r square. It is acting in the negative directions, so that is coming with the minus sign. Minus again because it is coming with the what, opposite to the direction of motion. So minus tau into 2 pi r into dx, right? That is equal to 0, right? Because what is my elemental area? What is my elemental area over which the shear stress is acting? This is my elemental area, right? That is my elemental area. What is the elemental area? Pi dl. Pi dl we used to write, right? And what is the pi d? Into L. But here is we are writing as length is what? Dx, that is delta x, and the radius will be diameter will be 2r, and that is how you are getting this term. That is equal to 0. And when you simplify that, when you simplify, you will be getting the final formula, which is obviously very important for further analysis. That is tau is equal to dou p by dou x into r by 2. Again, those who are not very much interested in derivation, you can ignore, but in my classes, I will not ignore, because at any point of time, a good question can be only be solved when you know the derivations. Now, once it is done, let me know. It's a very simple chapter. Laminar flow through pipe, through parallel plates, and third case will be cuvette flow. Once it is done, let me know. Done? Is it done? So now you know the formula. Now you know the formula. What is the formula? You know that tau is equal to minus r by 2 dou p by dou x. You know this particular formula. You know this particular formula. Tau is equal to minus r by 2 dou p by dou x. So here, my dear friend, what you can further write, that this is a pipe, capital R, capital R. You have taken the small elemental area of small r, and from the wall, everyone know that y is a distance from the wall. So y plus small r is equal to capital R. So dy will be what? Minus of dr. This is what they have written. Dy will be equal to what? Minus of dr. So now you know that relation, right? Tau is equal to what? Mu into du by dy. Now du by dy you replace with the dou u by dou r. That will be coming with the minus sign. And now you try to equate this tau with this tau. Both are equal. So when you do that, you will be getting final one like this. Make a note of it. Now what you do? Integrate it. You just what you do? Integrate it. When you do the integration, what you will be getting? 1 upon 2 mu dou p by dou x, integrating with respect to r, obviously, right? We have the variable r, so I'll be integrating with respect to that. R square by 2 plus c. That is my first equation. This is constant. Y is varying, small r is varying, not a capital R. So dr will be 0. Differentiation of that will be 0. Right? Because of dou p by dou x sum only, what you are thinking that because of this only we are supplying with the help of pump. We are sending the liquid in a pipe with the help of what? Pump only. That's why the pressure variation is there. That's why this difference is there. Otherwise, if there's a no flow work difference, then do you think that big industries need the centrifugal pump or any pump? Tell me, guys. If there is a no head loss due to friction, what will happen? Do we need any kind of pump or some other external sources to send the water in a pipe? Now, once it is done, let me know. Is it done for all? Done for all? This relation is from what? Newton, Newton's law of viscosity. Because whatever the fluid we are discussing, that is a Newtonian fluids. We are not bothering about the some non-Newtonian fluids. That is the that is not included in the Gates syllabus. Specifically in mechanical, also it is not mentioned, or in aerospace or in a civil, they have not mentioned anything regarding the non-Newtonian fluids. Now, once it is done, let me know. So what is the boundary condition? How to get the boundary conditions? How to get the C value? At r equal to r, we know that velocity will be zero. Everyone know that because no slip condition. Once again, you might be thinking, sir, hydrophobic fluids or maybe some other fluid which is having a slip condition for all. That is a PhD work. That is not there in the GATE syllabus, right? Now, so once you put that value that at r equal to capital R, when u is equal to 0, then what you will be getting? What you will be getting? I'm putting here u is equal to 0. That is 1 upon 4 mu. C will be minus 1 upon 4 mu dou p by dou x into capital R square. And after that, when you put C value once again into that equation, you will be getting this formula. And finally, you will be getting this formula. This is a very important formula. And what you are observing, I told you, right? In a fully developed region, velocity will only be the function of R. There will not be any X term. When there is no friction, no nothing, no source will be required. Directly water can flow because of its own energy. Because of its own inertia, it can flow. But if you need really pump, sometime you need the pump because you want to send the water to some higher level. You have the tank or some reservoir which are at some higher level than the ground level. For that case, you require to send the water energy to develop some potential energy that can be done by pump. Again, pump is not there in aerospace, so I'm not going into the deep of that. But if anyone interested, I will send that document or some textbook which is giving you the very basic idea of pump, right? Regarding centrifugal pump, we have the axial flow pump. Again, we have the what? A reciprocating pump. In your house, which pump is there? When you switch on the motor, you are supplying the water. You are sending the water to the what? Tank, which are there on the top of your roof from the ground level, right? From the ground level, whatever the water is there, which is being sent to the top of that with the help of which pump? I told you name of three pump, right? One is centrifugal pump, reciprocating pump, axial flow pump. Centrifugal only. Have you ever thought why we used only centrifugal? Of course, why you will think as an aerospace engineer, but still, when we have many pump, then why we are using specifically that one? We are using because it can handle a huge amount of mass flow rate, or it can send a very huge discharge at a particular section, right? But suppose if you are sending the water in agricultural, those who are related to agriculture background, there you will see the reciprocating pump, because there we need to send the water from very ground level to the surface level, right? So we need their high pressure ratio, not the huge amount of water discharge quantity. Here we are not having the building height like a 10 floor or 20 floors, right? So we don't need that one. Only one pump is sufficient, that is centrifugal pump. Even if your house or whatever the roof where you have the tank is at the very high level, like a money house, then what will happen? You need to install two pumps or three pumps in a particular what? Which combination? Series or parallel? When you go to the money house, you will see not a single centrifugal pump. You will see centrifugal pump which is being connected in series combinations. If he will permit to enter, right, in their house. Now, so this is what the velocity profile you are getting by different when the flow is happening in a pipe flow. Now, next particular concept will be what is the relationship between the average velocity or maximum velocity. First of all, what is the maximum velocity? We know that this formula 1 upon 4 mu dou p by dou x r square minus r square. And this we are getting my different here from here. Now, what is the maximum velocity? Now, everyone know that the variation is what? Parabolic variations. This is parabolic variation. Now, everyone know that this particular variation is a parabolic variations. When this is a parabolic variations, the parabola will look like this, or the parabola will look like this. Now, at r, which we have taken from the center line, at r is equal to 0, when r equal to 0, you know that u is what? U maximum. Then what is the u maximum formula? This is what the u maximum formula. Which one will be correct? This will be correct. This is incorrect. Why it is incorrect? If I ask you, is it not the parabola? Or is it a hyperbola? How you will identify which is a better explanation, A or B? And what about shear stress? Just think about these two questions, and next will be shear stress. Shear stress, we know that mu into du by dr, minus of mu into du by dr. Now, if you want to calculate shear stress at the wall when r equal to capital R, then for that case, we have to differentiate this one. This one. What is du by dr? So 1 upon 2 mu dou p by dou x into small r. So 1 upon 2 mu into capital R. Because at r equal to capital R, this is my wall shear stress. And what is the final formula? Minus 1 upon 2 dou p by dou x into R. Now tell me how the variations are there. How the general variations? How the general variation of shear stress? Linear or parabolic? Linear or parabolic? Linear one, correct. Yes, very good. Yeah. So whatever the reason you are giving, that is correct. Only this particular figure is important. Figure B is correct. And shear stress variation is what? When I just multiply with the mu here, mu into du by dr, I will be getting tau, and that's how we are getting 1 upon 2 dou p by dou x into small r. How it is varying? R to the power 1. That means it is gonna have the linear variations like this. When at r equal to 0, the shear stress will be 0, and here it is varying like this. Note on these things. Done. All of you have noted down. Now you are getting some maximum velocity value that is at the center line, but I'm asking you, what is the average velocity with which what is the average velocity with which this particular all the layers hypothetically moving? What should be the value? Average velocity means we have to do the averaging of all the fluid layer velocity. Some is moving with some maximum velocity, some is moving with some uh, lower than maximum velocity, but on an average, with what velocity the fluid is moving in a particular pipe. Now, for that, we have to discuss the ratio of maximum velocity to the average velocity. Now, you know that what is the discharge formula? Discharge formula, everyone know that. Discharge formula, you know that area into V average. Area into V average, everyone know that, right? Area into V average, everyone know this is a formula we have. This is what the formula we do have, my dear friend, when the fluid is flowing in a pipe or in any section, channel section, area into V average is the discharge formula. But suppose we want to calculate in a pipe flow on an elemental area which is having at a distance r and having some thickness dr, then how to calculate dq discharge? Area will be 2 pi r dr into u. If I do the integration, I will be getting complete discharge at that particular section. If I do a small integration, if I do summation of all the small layer at a distance r having a thickness dr, if I do the integration, I will be getting the complete discharge. There is a no doubt about it. But the good question is that what is the variation of u? We know that area is what? Pi r square into u average. That will be equal to dq. That will be equal to what? 2 pi r dr from 0 to capital R. U will be what? Minus 1 upon 4 mu dou p by dou x into what? R square minus R square. Now do the integration and tell me what you are getting. Just do the integration and what you are exactly getting. Q. Total Q. So 2 pi you can take outside by 4 mu. Dou p by dou x is constant minus R square small r dr from 0 to R. Now when you do the integration, what you are getting? Just verify it whether you're getting this thing or not. Pi by 8 mu. Just check it out. Some 2 3 steps are there. Directly I have written this one. Pi by 8 mu minus dou p by dou x into capital R to the power 4 into capital R to the power 4. Once we know this one, we can directly equate to u average into pi r square. From here, what we are getting u average. U average, we know that we can get very easily 1 upon 8 mu minus dou p by dou x into capital R square. And that is how we are getting half of what? Maximum velocity. Because we know that u maximum is what? 1 upon 4 mu minus dou p by dou x into capital R square. So when you do the u maximum by u bar, or you will be getting 2. We are calling this to be u bar. That's a very simple, very basic fundamental we are going through. If you're not able to understand, please try to go through the mathematics, small elemental. When you do the integration, complete picture of discharge. It's a very basic procedure for getting any quantity. Take a small strip of element dr and the radius small r. You just do the integration. You will be getting from 0 to r. You will be getting complete picture of pipe. Again, don't say that, sir, minus r to r from here to here. No, it's a circular one. When you do from 0 to r, automatically you will get for whole one. It's a swept thing, right? When you just do the 360-degree, when you rotate your hand in a 360-degree, automatically you will get circle, right? If that is a rectangular section, then only we have to do from minus r to capital R if r is some dimensions of that channel section, other than circular cross sections. That's a very basic thing. I am assuming that you know all these fundamental things. Now, once it is done, let me know. Done. All of you have noted down. Make it fast. Now, note down the next concept: drop of a pressure for a given length of pipe. Now you will come to know why there is a drop of pressure. A very clear picture will be there in front of you. Now we know that average velocity u average, that is equal to, we know that 1 upon 8 mu minus dou p by dou x into r square, or we can also write minus dou p by dou x, that is equal to 8 mu u bar divided by r square. Now if I do the integration from 1 to 2, this is my section which I have been considering for flow through a pipe. Then if I just do the only analysis for this section, which is having a length of L, capital L, then I will be getting this formula. Simply put viscosity 0. Any difference is there? You only tell me. If fluid is having no viscosity and if it is flowing in a pipe, then there is a no pressure difference. Tell me, guys, what will happen? Total energy will remain constant or not? Already diameter of the pipe is fixed. Velocity cannot change, average velocity cannot change, right? Until unless you do have a segment like this. I'm not talking about this extreme case. I'm talking about a simple flow through a constant diameter pipe, which is having a fixed diameter. Diameter are not changing. And when it is a horizontal pipe, so there will not be any potential difference also. So I'll be getting this formula. Quickly note down, then we can discuss some problem regarding this. And one more thing, here you can just note down. Here you can make a note. U average formula or U bar we have written minus 1 upon 8 mu dou p by dou x into r square. Rather than writing this formula, let me write velocity at any layer r minus 1 upon 4 mu dou p by dou x r square minus r square. Again, I'm simplifying this one, minus 4 mu dou p by dou x r square 1 minus r by r whole square. What is this? U maximum r by r whole square. So sometime in examination, they will give the velocity profile like this instead of like this. This one. Both are same. In question, if I mention the velocity profile is linear one, rather to say parabolic, if I say it's a linear one, like this, then what you will do? What will be the relationship between the U average and U maximum? You please derive as a homework. Just make a note of it, then I will discuss about that. So please do not neglect any topic. Again, my humble request, any topic you cannot neglect for gate examination. Anything can be asked. From the derivation, we know that. From the derivation, we know that it's a parabolic variations. And we have seen also. But indirectly, forcefully, they are making us to assume that the velocity profile is linear one in the problem. We have to assume it's a linear one. We can apply the Bernoulli in a center line streamline. Which one you are saying? You're talking about this one from 1 to 2. No, ideal Bernoulli equation we cannot apply. We have to apply the Bernoulli equation with some losses. That is a modified Bernoulli equations. Getting my point? See, in that case, if there is a no viscosity, there will not be any boundary layer formation at all. If there is a no boundary layer formation, there is a no question of applying inside the boundary layer or outside the boundary layer concept of Bernoulli. Right? See, the reason of boundary layer I will discuss in tomorrow's class. We have huge discussion on this boundary layer only. When you have the viscosity, see, whenever any fluid is flowing, for example, you can consider pipe case as a two flat plate. When the fluid is flowing with some zero viscosity, whenever the fluid is coming in contact, whenever the fluid is coming in contact with the uh, fixed plate, definitely its velocity will be zero. Definitely its velocity will be zero to satisfy no slip condition. Let's say, for example, above layer is there. How that layer, second fluid layer, will come to know that velocity 1 has been rested? You only tell me. If there is a no messenger, this is a messenger. If there's a no messenger which is passing the message from the wall to second fluid layer, from first fluid layer, that I am at the fixed position, you also please try to slow down. If there is a no messenger, no viscosity, there will not be any boundary layer formations. There will not be any boundary layer formations. Simply, it will violate the no slip conditions. Right? Getting my point? What one? Which one you are saying? Meanwhile, all of you, please done with this. No, why you will apply the modifications? Why you will apply the modify Bernoulli equations? Simply total energy will conserve here and here. Point number one, point number three. In fact, point number three also. You okay? I understand. You are talking about developing region. In the developing region, central line velocities keep on increasing. You can apply the Bernoulli equation between one and two at this one. That ideal Bernoulli equations that you can apply in a central core region. This is a central core region which has not been affected by the what we call theory Bernoulli, that is boundary layer theory. So we can apply the Bernoulli. There's no doubt about it because that region is outside the boundary layer, so we can apply. I thought you were asking this developing regions, developed region, but before that, yes, we can apply. See how you can justify there also in a central line. See at section 1 and section 2 in a developing region, here velocity is what less, here velocity is more. Velocity is less, velocity is more, but pressure is more, pressure is less. So both the terms, kinetic energy, potential energy, they are summing together in such a way that total energy remains constant. Although the potential energy will not vary as the point number 1 and 2 are on the same line. Getting my point? Yes or no? So this thing has been clear. This particular formula P1 minus P2, that is 32 mu U average into L divided by D square. Once we have clear with this formula, you try to do dividing by rho g. When you divide by rho g, you will be getting head loss due to friction. Because why we are doing that by rho g? Because P1 minus P2 will be having a unit of Newton per meter square, and rho g is nothing but what, kilogram? Sorry, rho g is what? We have the unit Newton per meter cube. So this will cancel out. I'll be having the unit in terms of meter. So that is known as Hagen-Poiseuille equation. This one. The flow cannot be developed on flow over the flat plate. Whenever the fluid is flowing over the flat plate, the flow cannot be developed because we don't have any condition call from both the sides. Let's say this is my plate and the fluid is flowing over that plate. We don't have any imaginary plate such that the boundary layer is growing like this, and from here also the boundary layer is growing like this. Nothing called such a facility. So boundary layers keep on growing here. So definitely there will be only developing region rather to say developed region there. So we don't have any fully developed region for the flow over the flat plate. Now once it is done, let me know. So here you are getting this formula. This formula is valid for only laminar flow. It is only valid for laminar flow. What will happen if the flow is what fully developed turbulent flow? This particular formula is not applicable because this formula has been derived while assuming U average from here. And this formula is there only for laminar flow, not for the turbulent flow. We don't have any parabolic variation in the turbulent flow. We have these logarithmic variations. No doubt. In practice, it is convenient to express the pressure loss for all the types of fully developed internal flows, whether it is a laminar or turbulent, circular or non-circular, smooth or rough surface, inclined or horizontal, by using this formula. FLV square divided by what? 2D. No, it is only valid for developed regions. Whatever the formula we have just seen, that is for developed region. Because here what we are doing, we are assuming that, see, this formula has been derived while taking by what? When you see the derivations, dou p by dou x. This dou p by dou x we have taken outside the outside of this integral because we are treating this to be a constant one. But in our developing regions, we have these variations in dou p by dou x, and those things we are not discussing in a BTech level or MTech level. We only study in PhD level, right? So now here, when you note down this formula is applicable for all laminar, turbulent, but fully developed only, right? Circular, non-circular. Make a note of it. Rather to say D, you better write hydraulic diameter. Hydraulic diameter. And what is the formula? It's a very similar formula what we have discussed. 4 into cross-sectional area by perimeter. Of course, for the flow through a constant diameter pipe, here the DH will be D for a circular pipe. F is Darcy friction factor. F is Darcy friction factor. Done. Now, try to solve this question and let me know the answer. Two pipes of uh, constant sections but different diameter can carry the water at a same volume flow rate. The Reynolds number based on the pipe diameter will be what? That is nothing but you know uh, open channel flow. When the water is not fully filled, that is a different segment. That is a civil topic actually, open channel flow. In that case, what will happen? What do you think? We will be very much tempted to think that as there is a no upper half of the water, so there is a no boundary formations. So, but is that true? See, open channel flow also, you might be think that sir, there is a no uh, upper portion of the water which is being surrounded by this upper wall or maybe this surface. So you might be thinking, sir, that that can also have the continuous developing region. There will not be any fully developed region. But again, that is not the true statement. That is not the correct statement. We have this fully developed open channel flow also. Getting my point? Understanding? In open channel flow also, whatever the discussion is there, that is discussion for a gate syllabus of civil engineer, includes only for fully developed region, not for the developing regions, right? It has nothing to do with the contact of the water with the wall of the pipe to have the boundary layer formation and to say from both the sides the boundary layer has been developed. Here also, in this case also, it will be developing from both the sides. Getting my point? Then only we'll be having the fully developed open channel flow. Otherwise it is not possible. Again, that will be a vague discussion for our case, because we are not going to deal with that open channel flow. Now here in this question, what you will think, the two pipes of different diameter carry the same flow rate q and q. The Reynolds number based on the pipe diameter will be what? Rho vd by mu. Here we can write like this: v1, this say, let's say the diameter is what, d1. Reynolds number for the pipe 2 will be rho v2 d2 by mu. Now tell me guys, what will happen? When the discharge is same, then A1 V1 will be equal to A2 V2. But here the diameter of pipe 2 is lesser than pipe 1. Then definitely velocity 2 will be more than velocity 1, right? If there is a velocity variations, you try to convert this formula in terms of discharge. So we can write V as what? V we can write Q by area, that can also be written as 4Q divided by pi d square. So 4Q divided by pi d square into d divided by mu. So Reynolds number is what? Inversely proportional to what you are observing, diameter. So when we have more and more diameter, if the diameter is more and more, Reynolds number will be lesser and lesser in that particular pipe. So in a narrow pipe, when the diameter is lesser, the Reynolds number will be larger. Try to solve this question. Two overflowing reservoirs are connected by the pipe having a length of 100 meter and cross-sectional radius of 0.02 meter such that the height difference h remains constant as shown in the figure. The center line velocity in the pipe is 10 meter per second. The velocity profile in the pipe over the entire length is given by this relation. Dou P by dou x is a constant pressure gradient along the pipe length. X is measured from the left end of the pipe along its central axis and is radial location inside the pipe with respect to its axis. The given data has been as density as well as kinematic viscosity respectively. If all other losses except frictional losses is neglected, the value of h they are asking. So what you do, we can apply the Bernoulli equations between 1 and 2. Applying between 1 and 2. Of course, we have the fluid which is having some viscosity, so we have to apply modified Bernoulli equations. P1 by rho g, V1 square by 2g plus the reference, suppose height is from here to here, let's say Z1, and here to here, that is Z2, plus head loss due to friction. P1 by rho z, P2 by rho z, both will be 0. Both are subjected to what? ATM pressure, P ATM. V1 will be 0, V2 will be 0 because open tank, that is a big tank of, we can assume that the diameter is infinite of that tank. Z1 minus Z2 will be what? H, that is equal to head loss due to friction. Head loss due to friction, we know that 32 mu u average by rho g d square. That's a very simple formula, we know that. Yeah, that is correct answer. And of course, how you come to know that the flow is laminar, even though you uh, have not calculated anything about the Reynolds number because of these relations. This is only valid for laminar flow. HF will be 32 mu. So they have given the kinematic viscosity, so we can write instead of writing the mu, we can write uh, mu is what? Mu by rho. So mu can be written as kinematic viscosity into density. Kinematic viscosity is what? 10 power minus 6. Density is what? 1000. U average, that is a question mark. Length is what? 100 meter divided by rho g. What is the rho? 1000. G is what? 10. Diameter. D is given as 0.04 meter. So when you calculate, for calculation you need U average. But they have given the center line velocity 10 meter per second. That is the maximum velocity. Because when you make the parabolic profile, you will be having a center line velocity when r equal to 0, correct? That is given as 10 meter per second. But for a laminar flow, you know that u average is u maximum by 2. So that is 5 meter per second. So put that value as 5 meter per second. When you calculate, you will be getting 1 meter. You can get dou P by dou x from maximum velocity formula, 1 upon 4 mu dou p by dou x into capital R square. You know every data, from there you can calculate. Once it is done, let me know. Yes, that is correct. And that is how you have the difference in the water level. Why there is a difference? Because of viscosity. If viscosity is also zero, then both the pipe is connected, the liquid is flowing, and completely liquid is rising in that tube. There is a no water difference will be there. No h, small h. As you have these some losses, had losses, that's why you're getting the small h height, which is being lesser than the previous reservoir height. Now, note on the next segment. Yeah, try to solve this question. A water enter into the circular pipe of length 5 meter and the diameter is taken as 0.2 meter, with the Reynolds number is nothing but 500. The velocity profile at the inlet is uniform and it is parabolic at the exit. That means inlet velocity profile when it is coming in contact, before coming in contact, it is having some u average, uh, and at the exit we have this variation to be parabolic variations. Rho into u average into d by mu. Reynolds number does not depend on the velocity profile, it depends only on u average value. U average value will remain same as long as, let's say you have section 1, section 2, A1 V1 equal to A2 V2. A1 is same, then V1 and V2 has to be same. V average at 1, V average at 2 have to be same. That means at the inlet, row average, at the outlet, row average, row is same, D is same, mu is same. Then who will change the Reynolds number? No one, right? Because of mass conservation, that is a basic fundamental principle of fluid mechanics. If it is other mechanics, we can afford to have some losses in the mass flow rate. But as long as we are discussing fluid mechanics, there cannot have any other thing other than mass conservations. Mass cannot go anywhere. It has to conserve somewhere. Now, once it is done, let me know. Is it done? Done, guys? Now, try to solve this question as a homework. This question, I will share the slide from there. You can see, or you take the picture of this question. Till what time we have the class today? Try to solve this question also as a homework and tell me the answer. While coming for tomorrow's class, we'll discuss. At what time we have the class today? 5:52. What is the timing? 7. No. 8:50. So you don't have any other class today after this? Note on the next case, laminar flow, case number 2. Laminar flow in between two fixed two fixed parallel plates. Fine, fine. Okay. So note on the next segment, the laminar flow between two fixed parallel plates. The fluid is flowing inside the pipe. Y is the distance from the wall, lower wall. And if I take any fluid element at a distance y, any fluid element, at a distance phi, having the let's say the thickness to be dy, and if I zoom it, I will be getting this is dy dx, for example, and I will be getting here the pressure value. Let's say pressure is what, p into dy into 1. Width I'm assuming to be 1. Width I'm assuming it as 1 unit. Here, what about the pressure? P plus dou p by dou x into dx into dy into 1. Shear stress. Unlike what we have discussed, the shear stress that is acting in the circular pipe opposite direction, but it is not the case over here. Because when you take the fluid element like this, when the fluid is flowing like this, what will happen? This fluid layer which is being attached to the top plate, it is fixed one. When the fluid is flowing, what will happen? Fluid will, let's say the fluid interaction between 1 and 2, like here, what will happen? Tell me this. When the fluid will be start flowing, when the fluid will be start flowing, then what will happen? The moment the fluid will be start flowing with some velocity u, then definitely this plate will offer some kind of resistance onto the fluid layer like this. The fluid layer being subjected to what? Shear force offered by the lower plate. The fluid layer which is being over here, they will also try to move forward like this. Then what will happen? There will be some forces offered by which one? Top plate onto the second fluid layer. In which directions? In which direction? Tell me guys. In this direction? Yes. When this fluid will be flowing, right, when the fluid is flowing and this is also moving forward with the higher velocity, then this fluid layer will offer this basically forces onto this third fluid layer. In which directions? See, let me just make once again the fluid layer which I'm making over here. This is the fluid layer. What will happen? This is moving with some higher velocity. So, and this fluid layer which is being attached, right? This is also being resisted by the top plate. The moment they will try to move forward, the top plate will offer some kind of resistive forces onto the what? Fluid layer, right? No, just wait. This thing we have discussed in our first class. Tell me, guys. Option A for the fluid element, this dy, whether this is correct. C option will be none of the above. Which is correct? We have discussed in our first class. That is a basic concept what we have discussed in our first fluid properties. There also we have discussed this concept. Now it's better that if I just remove it and let me draw once again. A fluid layer I'm assuming over here like this at a distance y. Now tell me for this fluid layer which are there at a distance y here from a fixed plate, what will happen? Tell me guys. Now think very carefully. It's not as that simple as you might be thinking. Just recall what we have discussed. How the C is possible. In any circumstances, whether C is possible. See guys, understand when I draw the this full view of that, try understanding very carefully. Here I have taken the fluid layer. What is happening? This fluid layer is moving with some velocity u, and here we have the plate like this. For example, above that fluid layer is moving with some higher velocity than this one, u plus du. Check it out. Is this the condition is happening? No, the direction of flow is from uh, here towards the positive x directions. What I'm saying, when the fluid is flowing and whatever the element I have shown in the figure, right, it is just a point. It is just a fluid element which I'm taking, but for make of to have understanding of that fluid element, I'm just making it like a cubical box so that you can understand the fluid forces which are acting on a particular fluid element. This having zero velocity. Now, which is having the more velocity, u or zero? U. Then what will happen with the plate? Plate will offer some kind of forces in which direction? In these directions, like this. To slow down that speed, it will offer some kind of forces in these directions. What will happen with this fluid layer and the fluid layer which are moving with some higher velocity? When the fluid layer which are moving with some higher velocity and this fluid layer which are moving with some u velocity, this fluid layer which are just attached to this plate, what will be they will be saying? They will be offering some kind of resistance like this. Same resistive forces will be developed by this u plus dv onto this fluid layer in these directions. That's how the variations will be there. But here you have the variation with respect to dy. So here we have tau into area, let's say dx into 1. So here you will be having tau plus dou t by dou y into dy into what? Dx into 1. shear stress into area. No, 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 no. How it is? There is a no nothing called rotation. Here there is a no symmetry, right? Just like what we have seen in the what you call circular pipe. Here we don't have any nothing called symmetry. In a circular pipe also, the no fluid is rotating. There is a no swirling motion. We are not providing any kind of things, rotation at all. Getting my point? Here also no rotation. There also no rotation. It is just a symmetry. Getting my point? In a circular pipe section, it is just a symmetry. See, I think I need to make the 3D figure of that. This is the element, circular element. Circular element is what? Circular element will not have the surface like this, right? A different surface, the top surface and the bottom surface. It will have total one surface only, not two surface. Here we'll be having only what? You have this no, basically surface, only one surface in a circular segment, and all will be resisted by what? Tau only. Not only this one, you will be having tau here also, backside also tau, same tau will be there. Getting my point? Right? No, 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 nothing concept of torque and all. We are not discussing about any swirling motion over here. We are not providing, no, nothing is there. V theta. V theta 0, VR is 0. Only we have Vx, that is U, that is minus 1 upon 4 mu dou P by dou X into R square minus R square. That is what we have the formula. We don't have any V theta, no swirling motion, no VR is there. Only we have only X component, that is this X component. V is there. That's it. Now, getting my point or not, all of you? Why there is a different direction of shear stress? See, directly I can write the formula, I can close the chapter. But why I'm stretching too much? Whether you are understanding or not, a rectangular element. Why we are making this as a rectangular element? Why not we are making circular element? Because it's a very common sense. When the plate is when the fluid is flowing in a plate, which is like this, in between that the flow is happening, then I need to assume that is a shape of like this only, right? How can I assume the shape to be circular one? When the fluid is flowing in a circular pipe, definitely I need to take the circular cross sections like this. This surface and this surface both are different in the circular. Or whether your imagination is very, very weak. Can't you imagine these are the same? One, two, three, four. Same one surface only. But in case of rectangular one, it is not. One, two, three, four, fifth, and sixth backside. All are different surfaces. Getting my point, all of you. Yes or no? Is that clear? Now, these are the very basic thing, and definitely when you see the textbook, directly they are writing without giving any hint or anything telling you before telling you anything, they will be directly writing these things. The direction of say stresses. So this is correct. Now, once this is correct, so again what we have to apply? We have to apply net force, that is mass into accelerations. Once again, acceleration will be what? U into dou u by dou x plus dou u by dou t. Steady flow, no variation in x directions, so that is 0. So acceleration will be 0. So net force, once again we have to keep it what? 0. Once you do that, what you will be getting? Sorry, tau into what? Dx into 1, because this we have dx, this we have dy, and the width I am taking, what? Width I am taking it as 1 unit. P into dy into 1, p plus dou p by dou y into dy, dx, sorry, dou p by dou x, because we have the variation in x direction, right? Dou p by dou x into dx into dy into 1. Now you do that summation of forces. net force in the direction of motion has to be 0. Those who are having problem with the derivation, again I'm telling you, you simply close your eyes. The final formula is very much important rather than these derivations. But if something else they will ask, through the derivation you can hit that question very quickly. P into dy minus p plus dou p by dou x into dx into dy into 1, because area is what? This is the area, right? Dy into 1, that is the area on which it is acting, plus t plus dou tau by dou y into dx into 1 minus tau into dx into 1. So when you do that, you will be getting d tau by dy dou p by dou x. Tau, we know that Newton's law of viscosity, du by dy. Put over that, you will be getting d square u by dy square 1 upon mu dou p by dou x. Equation number 1. Tomorrow we will continue from equation number 1. Whatever the equation number 1 you are observing, whatever the equation number 1 you are observing, that equation number 1 you can get very clearly from the Newton's second Navier-Stokes equation also. What is the Navier-Stokes equation? In x direction, mass into acceleration, that is max, is equal to what? You have the formula something by mass, so I can write here it as u into dou u by dou x plus dou u by dou t. V0 omega is 0, dou u by dou x is 0, because fully developed flow, that is equal to minus dou p by dou x plus mu del square u by dou x square del square u by dou y square plus body forces bx. There is a no body force in x directions. There is a no dou u by dou x, dou u by dou t is 0. So dou square u by dou x square will also be 0. There is a no variation in z directions of u, that is also 0. So final formula will be what? Mu into dou square u by dou y square, that is dou p by dou x. So either you can get from here or you can get from here. In both the way, both are correct. From here, what will be the velocity profile, whether it is a parabola or linear, that we will discuss after doing the integrations. How many times? 2 times, because first time when you do that, you will be getting dou u by dou y. Second time when you do that, you will be getting what? U, right? Just note down. Once it is done, we can leave for the day. Done. Done, guys. Yes. Tell me, guys. Done. No response.
Hello, hello.